Welcome to part 3 of indeterminate forms and L'Hopital's rule. Example 4 says find the following limits. We have the limit as x approaches 0 of 1 minus 2x, all raised to the power of 1 over x. And if I were to use direct substitution, we would essentially get 1 to the power of 1 over 0, which is another way of saying 1 to the power of infinity, which is one of our alternative indeterminate forms. And so we want to utilize some various techniques. I'm going to start off by saying let capital L equal the limit that we are trying to find. I don't know what capital L is. We're just hoping that it's a number so that we can try and find it. At this stage, what I'm going to do is I'm going to take the natural log of both sides of this equation. This should look kind of familiar because we did something similar when we were doing logarithmic differentiation. And the reason that we're taking the natural log is so that we can get the function outside of the exponent. Now, at this stage, we get that the natural log of capital L is equal to, and we saw a theorem earlier on in the class that allows us to swap the limit and the natural log. So now I have the limit as x approaches 0 of the natural log of 1 minus 2x to the power of 1 over x. And now what that's going to let me do is use the power rule for logarithms. So I get that this is the limit as x approaches 0 of 1 over x times the natural log of 1 minus 2x. And if I were to use direct substitution at this point, I have 1 over 0 times the natural log of 1, which is 0. So essentially, this would give me the indeterminate form 0 over 0, which means that I can use L'Hopital's rule at this point. And I'm just going to rewrite this function so that it looks like that. And now I'm going to apply L'Hopital's rule. The derivative of the numerator is 1 over 1 minus 2x, and then I need to use chain rule and multiply by the derivative of the inner function. And then the derivative of my denominator is equal to 1. So let's simplify this a bit. I have the limit as x approaches 0 of negative 2 over 1 minus 2x. And if I were to use direct substitution now, I would get negative 2 over 1 minus 0, and so that ends up equaling negative 2. Now, we have to be careful at this stage because that is not actually our final answer. If you remember from earlier, we have the natural log of L is equal to negative 2. So L is the thing that we are trying to find. We have the relationship again. The natural log of capital L is equal to 2. And I want to solve that equation for capital L. And, oops, I forgot the negative sign. So this should be negative 2. And now what I can do is I know that this relationship is true. And so that implies that capital L or our limit, is equal to e to the negative 2 power. And this represents our final answer for part A. Example 4, part B, wants us to find the limit as x approaches infinity of 1 plus 2 over x, all raised to the 3x power. Now, if I use direct substitution, we end up getting 1 plus 0, so that's 1, and then to the power of infinity. So this is one of our alternative indeterminate forms, but we want to get it into a different form so that we can use L'Hopital's rule. And we're going to apply a similar strategy to part A. So I'm going to say let capital L equal the limit that we are searching for. And now I'm going to take the natural log of both sides again. So I have the natural log of capital L is equal to the natural log of the limit as x approaches infinity of 1 plus 2 over x raised to the 3x power. And I know that I can swap the limit and the natural log from the theorem that we referenced earlier. And I'm just going to apply the power rule now. So I have 3x times the natural log of 1 plus 2 over x. If I used direct substitution at this point, we wouldn't end up getting one of the indeterminate forms that we are looking for, because again, we are searching for 0 over 0 or infinity over infinity. And so what I'm going to do to help us get there is, this is a previous technique we've used. I'm going to change that 3x and I'm going to move it to the denominator so that we can get one of our desired indeterminate forms. So I'm going to move it to the denominator by dividing by the reciprocal. So I have 1 over 3x. And now if I used direct substitution, we would get the indeterminate form 0 over 0. So let's apply L'Hopital's rule now. This is going to equal the limit as x approaches infinity of 1 over 1 plus 2 over x, and then I need to multiply by the derivative of the inside. And so that would be negative 2 over x squared. And then the derivative of the denominator. If it helps, you can think of this as 1/3 times 1 over x. And 1 over x is the same thing as x to the negative 1 power. So if I wanted to take the derivative of that using the power rule, I'd bring down the power of negative 1 times x to the negative 2 power. So my derivative over here is negative 1 over 3x squared, like that. Okay, so this is equal to the limit as x approaches infinity of 1 over 1 plus 2 over x, and I'm multiplying that by negative 2 over x squared, and I'm going to take my denominator and multiply by the reciprocal of that now. So that would be negative 3x squared over 1, and what's going to happen is this x squared and this x squared will divide out, and we get that that's equal to the limit as x approaches infinity of negative 2 times negative 3 is positive 6. And then my denominator, it looks like it's staying the same. And at this point, I can start to take the limit 2 over x as x goes off to infinity. That goes off to 0. So this ends up being 6 over 1, or just 6. At this stage, remember, we have that the natural log of capital L is equal to 6, and I can do this with e as the base, and that implies that capital L is equal to e to the 6th power, and that is our final answer for part B.